Now I'm going to work some examples on assigning causality, and in the interest of keeping this video short, I'm going to be presenting, as you can see here, a model in a schematic form along with a completed bond graph, and it would be a good idea as you review these to make note of them and to use these as exercises, see if you could build the bond graph. But what we want to focus on here is just on the causality assignment procedure in application, and also in using causality to identify the system states. So we'll work through these for that reason at a good pace. So here we have a system that's a mass sliding with some friction on a surface here, so in 1 degree of freedom here, but we've got a spring and we've got a velocity source on one side of that spring here. So here's the model, here's the flow source that represents the velocity input, here's your spring element, and here's your mass. Again, once it's in bond graph form, it's really could be anything, but it does represent this physical system, as I'll show you in some other exercises here. You can actually show the relationship between mechanical and electric analogs pretty nicely this way. Let's just apply causality. Now remember, in the hierarchical approach, you look for any sources, then we look at how causality propagates into the system, and then we also want to maximize integral causality. So let's do this for this simple system here. Well, looking at the system, we have two energy storage elements, so we have possibly order 2, but we don't know until we apply causality. We have an input source here, so we're going to go ahead and apply integral causality on this bond here. So we have a flow coming in here. And now, once we make one assignment, right, we look to see how does it propagate into the system. Well, we have a zero junction here. And remember, at a zero junction, you can have as many bonds as you like that are specifying flow, but once one of the bonds specifies an effort, then the rest have to specify flow. We have not yet specified effort, so we do not have to make any decisions on any of the bonds at this point due to this application, okay? So what we would do here now is look for any other sources. There aren't any. So now we can move on. We're free to move on to energy storage elements. We have 2, and we could actually apply integral causality to either one of them, but we're going to go ahead and apply integral causality to the C, which remember is going to be flow into the C. So note that by applying flow causally into the C, I now have imposed an effort on that zero junction, which means this bond here also has to impose flow, which means I have to put the causal stroke on this side, right? Remember, this is power, but causality is flow. Causality, flow, causality, effort. Power is, again, telling you something totally different about the variables on these bonds. Focus on the causality. So now I've applied effort here. This bond is flow. This bond now is applying a flow here, but effort onto the 1. Since an effort on a 1 junction does not constrain any of the other bonds, I can now go to my other energy storage element and apply effort into the I element, which makes this also in integral causality. But now this bond is imposing a flow on that 1 junction, which means this bond has to be what? An effort, right? So remember, you can have as many efforts as you like, but only one can apply flow. On a 0, as many flows as you like, only one can apply effort. So now my causality is complete. So the only other step I want to show in these examples is identifying the state vector for the system. Well, we have 2 energy storage elements. They're both independent, which means here, right, the flow variable here is this is a spring, so it's got a displacement state, and on this mass I've got a momentum state. So this is an effort, this is a flow, but the state is p and x. So the state vector for this system, because these two are independent, are the two states of these independent energy storage elements, which are the x and the p. The next step that we'll look at later is deriving the equations for these two rate relations, but we're not going to do that here because we want to focus on practicing causality assignment. I've changed the system just a little here. I've added a force on the mass. I now have a spring and damper in parallel. I'm still putting a flow source in here. So the bond graph has changed a little bit. Again, on your own, as an exercise, you might see if you could come up with this bond graph. I may also add these two exercises for you to work on. In addition, in the future lessons, use these as homework problems where you would finish equation derivation, but for now we want to apply causality. We're going to begin looking for sources to begin with, but first, how many energy storage elements? We have 1, 2, the rest you have resistive elements and sources, no coupling elements. So the most the highest order we could have is 2. Let's see if we have that. We have a flow source, so let's start here. We could start here, but let's go ahead and start with the flow source. Again, you have specified a flow into a 0, so you're not constrained on applying causality on any of these other bonds. So that means we can then move to another part of the bond graph and look for other sources, and in this case we have to apply causality to this effort source because it is restricted, so we apply the effort causality into that one junction. Again, effort into a one junction, where we have not constrained ourselves, we still have freedom to apply causality anywhere else, right? So now we would look for any other sources. We'd see if that causality propagated. It doesn't at a one junction. So now let's go ahead and apply integral causality on that I, which means these bonds now are constrained to be efforts into this one. Now by doing this, we've imposed causality on this bond. Now we have a 0 junction with 2 flows. There's one bond left that must specify effort. We have one bond here that must specify effort. In doing this, now we've completed the causality here and now imposed the flow on this one junction, which means both of these bonds have to be flow coming out or efforts, right? Again, independent because they have integral causality. So this state for the spring, this momentum state, our system order is still, this is state vector, x and p, still order 2 as before. Right? We didn't change the number of energy storage elements, we just really changed the configuration of the system a little bit. Let's go on to the next example. A simple LRC circuit, series circuit. So we've got a one junction here with an L, C, and an R with an effort source. Causality is fairly simple on this one. We have an effort source here, so we'll apply effort onto this one junction. Now we can specify causality on any of the other elements. Remember, we always go for energy storage elements first. We never apply causality first on our element. Integral causality on the I, so that's independent. Integral causality on the C is allowed. And so we've got what charge on this capacitor, flux linkage on this inductor, and as expected, this is a second order system, so your state here is Q and lambda. Another electric circuit, LRC circuit again, but now we've got another resistive load in parallel to the C. So now that's the only effort source, so let's go ahead and apply on here. There's no other flow sources, so we apply effort again on one junction, not restricted. Let's go ahead and apply integral causality on the I. Now we've constrained these other bonds to have efforts. Now we've got a flow here flow coming into the R, that's okay. And now we can apply integral causality on the C. Now that's imposed the effort here, which means that R has to have effort in, which is the effort across that capacitor, which should all make physical sense. Okay, again, two independent energy storage elements, lambda, Q, two states, lambda and Q. Here's another circuit, slightly different. We've got voltage source here. You might try to build this bond graph also yourself, see if you agree. Again, we're focusing on causality assignment. 1, 2 possible states. Let's apply this effort source on the 0. Now we're at a 0 junction. We've imposed the only effort on there, which means both of these bonds have to specify flow or effort out, right? And now we can apply integral causality on that C, and note causality follows. State again is Q and lambda. Note that most of the examples to date have all had what we'll call full independent energy storage elements. There's no derivative causality so far, and so these all work out nicely. In later lessons, we'll look at some examples where you might have derivative causality or even algebraic loops. But for now, I want you to go through some simple examples and get a feel for applying causality if you have never done this before. Here's an example with I'm showing some analogs. It's a mechanical system and an electrical analog. What that means is that structurally they have the same configuration, and they would result in this very similar, what we call analog type equations. Although again, physically they're different, but they have a similar, what we call structure. They're going to have the same bond graph, right? Prove this to yourself. Again, another exercise in building a bond graph. Let's focus on causality. How many energy storage elements? We have 1, 2, 3. Is it order 3? Let's apply causality. There's no energy storage, there's no source elements, so we begin directly with energy storage elements. And let's go ahead and apply with this. Start with this I, with the C here. I've applied an effort on a 1 junction, which means I'm free to do whatever I want. I could go to this I or to this C, because it doesn't propagate, does it? Does that make sense? I hope it does. Let's apply causality on the C just to change it up. Now you've applied integral causality. That's independent. That's independent. Now we've got a 0 with an effort applied from this C, which means both of these bonds better apply flows, right? Now I've completed the causal assignments here. I need to finish with this I element, and because I'm free to apply, to specify flow into this one element, into this one junction, I can apply integral causality here, and then I finish there, and I have the third order system, with the states being the 2 displacement states and the single momentum state. Now a couple of generic exercises. Look at this bond graph. There's 2 effort sources, 3 R's here, 1, 2, 3, 4 I's. Now, I had actually meant for this I here to be an R, but let's look at it first as an I. And it's kind of unusual to have 2 I's on a 1 junction, because only one of them could be independent, right? Let's see what happens. Let's start with this effort source. 1 junction, which means I can apply integral causality. There's 1 independent state. Now I've applied a flow on this 1 junction, which means these 2 bonds have to be efforts, and that's complete here, but now flow is propagating into the 0, and so I'm free to move wherever I want now. So I need to go to the next effort source, effort, right? Now I can apply integral causality on this guy, and that's my second state. So this is, let's call this P.2, right? Second bond, P.8. So I've got two states so far, P2 and P8. So my state vector so far is P2 and P8. I'm going to wait because I want to order them. I suspect I'll have another independent state here. So I've applied a flow here, so now I can have these bonds that apply efforts, right? And note, another flow into this zero, I have two bonds unassigned, so I don't have to yet apply any of these yet. Or, again, I do not specify that causality yet. I need to go to my next source. Effort in, 1. So now I go to one of these I elements. Let's go to this one. So it's P dot 11. Right? So actually P8 is my second state, and so is P11. Now in this configuration here, once I specified that flow in here, now these would have to be efforts, right? Which means if this was an I element, then the P dot 12 here would not be a state, right? P12 is not state. So it's derivative. This isn't derivative causality. Now I've got a flow coming into the zero, flow here, which means this one better specify effort. And I'm okay at the very end specifying the resistance causality here. Okay? And I'm done. And I would have a derivative causality. Now if I had actually intended for this to be a resistive element, that would have been okay, but it was good to show you that, oh, you might have a derivative causality, and now, again, you had 1, 2, 3, 4 energy storage elements, but really your state order was 3. Another generic exercise. Let's move through this one quickly. Effort here, effort here. I have 1, 2 energy storage elements, a lot of 3 resistive elements, an ideal coupler here. So let's start. Oh, sorry, there's an I element here, so 3 energy storage elements. So there's a there's a input effort source. Let's go ahead and we stopped there, so we don't have to make any other causality assignments on this one. So we need to come to our other source element. Again, an effort on a one junction, no constraint on any of these other bonds. So now we need to look for energy storage elements. I'm compelled to come to this guy up here, and now applying a 0 here, this is now integral. I have to apply effort out here and out here. And note that now that I've got an effort into this T, it's got to be effort out of the T, right? Remember this, the T element, the transformer has constrained causality. Once you specify one side, the other is known. So let's look at the consequence of both of those causal assignments. I've got 2 efforts on a one junction, which means this R is what's specifying the flow on this one junction. So all this is done. I've got another effort on this one junction, so I am free to apply causality on any of these, and to have one of these apply the flow, and the one that I choose is the I element because I want integral causality, right? Finally, the rest of these have to be effort, which means I have integral causality on the first C here, on this C, on this I. So I have 1, 2, a third order system, right? So I number these 1, 2, 3, 4, 5, 6, say 7, 8, so 7, 8, 9, 10, and then 11. I see that my state vector would be, all these states would be what, Q5 for this guy, P7, and Q11, third order. Now again, these are the 3 state equations that I would write. Here's a little example that has a little linkage between 2 masses and a spring and damper. Here's the bond graph. Again, another good exercise for you to practice with. There's an input force here. Here's my effort source here. Here's my mass element here. Here's another mass element, and there's a spring. You can finish out, and again, you should check this bond graph. Make sure that you're starting to practice and that you're starting to feel comfortable with these. Let's start off again with our input force. At one junction, I'm free to go anywhere. I've got to apply causality to my energy storage elements. Let's go ahead and just continue here. Now I've specified the flow at that one junction. Those are efforts. That flow now going into the T means the flow is coming out into the zero, which again does not constrain any of the other bonds yet, so I can apply integral causality on that C, which now does apply that effort source on that zero, which means this bond has to be flow in to the zero. Finally, I've got two bonds left. Integral causality specifies the one, and I'm done. So I've got 1, 2, third order system with the respective states of those elements forming the state vector. Last example in this set is a little circuit here with another ideal coupling element. Here's the transformer here. You got a voltage source, resistor, capacitor in parallel, and then an LRC circuit. Okay, so 1, 2, 3 energy storage elements. Again, this is going to come out independent, I can expect. Let's see the input effort at the 1, so I'm free. Again, you don't focus on resistive elements, go to the energy storage elements. Let's go ahead and apply effort at that zero junction, which gives flow into that C, and that's independent. Now effort comes out of the zero, right? And at this one junction, two efforts means this R specifies the flow at that one. And I'm done there, done there. Effort across that T puts an effort at that one junction. So now I can apply integral causality on both of these elements, and I've got another third order system. So hopefully these examples have taken you through the process of how to apply causality. In the next lesson, we're going to begin looking at how we take the next step, which is using causality to help us derive state equations.